Hello students, I welcome you all in the quick solution of All India AIATS test series for JEE Mains 2020, test number 2, code E and F, subject physics, test dated on 17th of November 2019. Let's start with the question number 1 now. Here in question number 1, a copper cube of side A is heated and then allowed to cool in an evacuated enclosure. It takes time t to cool from temperature θ1 to θ2. Now another cube of side L is placed in the same enclosure and allowed to cool. Now the time taken to cool from θ1 to θ2 is found to be 3t. Assuming Newton's law of cooling to be applicable here, the value of L is. We need to find the value of L in terms of A. Well, what we know here is the rate with which the temperature decreases. It actually depends on the total exposed surface area divided by mass, and if the density to be taken as constant, then exposed surface area will be proportional to the square of the side length. I would say proportionality constant, let it be A. It will be depending upon A square, and the total volume will be depending upon A cube. So effectively we shall say the rate of decrement of the temperature would be minus of K by A. This is the way the temperature will be changing. So now here in the first case, the temperature decreases from θ1 to θ2, that is θ1 to θ2 in how much time? In time t. I would say it will be minus of K divided by A, and in the second case it is θ1 minus θ2 divided by, it takes 3t time, this time it is minus K by L. Taking the ratio of these two parts, we shall have here 3t divided by t is equal to L by A, or I would say L is equal to 3A. Looking onto the option for question number 1, option 1 is the correct answer. Now let's proceed to question number 2. In question number 2, there are 10 moles of monatomic gas at temperature T in a cylinder. Heat is rejected by the cylinder such that temperature remains constant, but 4 moles of monatomic gas gets converted into diatomic gas. The decrease in total kinetic energy of the gas sample is. Total kinetic energy now would be the total internal energy of the gas sample itself. Initially there was 10 mole of monatomic gas, so 10 into 3 by 2 RT, this will be the initial internal energy of the system. In the final state, we shall remain with 6 mole of monatomic gas, 6 into 3 by 2 RT, and plus 4 moles of monatomic gas gets converted into diatomic gas, so we shall remain with 2 moles of diatomic gas. It will be 5 by 2 RT. This will be the final internal energy of the system. Just see how exactly this one is for. This will be 5, so 15 RT initially, minus, this is 3 into 3, 9, and here 5, so it will be 14 RT. So this is the change in internal energy, and that the value comes out to be RT. So for question number 2, option 3 is the correct answer. Now let's proceed to question number 3. In question number 3, 2 moles of monatomic gas gamma to be 5 by 3 is mixed with 3 moles of diatomic gas gamma, there is given as 7 by 5. The value of molar specific heat at constant pressure P for the mixture is. I'm just taking this straight away, its definition. If delta Q is the heat supplied at constant pressure, it must be taken as N1 Cp1 into delta T, N1 being 2, Cp1, it's monatomic gas, it will be 5 by 2 R into delta T, and here N2 is 3, Cp2 is 7 by 2 R delta T. This is the total heat supply. So specific heat capacity is total number of moles, this time it is 2 plus 3, 5 delta T. This is 5 delta T. So that is the specific heat capacity for the system there. I would say delta T will cancel out here. This 5R from this side, and plus this is 21 by 2R, or effectively 21 plus 10, it will be 31 by 2R. Here we were having the one denominator term 5, so it will be 5 here, or effectively 31R by 10. We are getting option 4 as the correct answer, that is the specific heat capacity at constant pressure for the combined system. Now let's proceed to question number 4. Here in question number 4, a parallel plate capacitor C with plate of area A and separation D is filled with liquid of dielectric constant K. The level of liquid is D by 2 initially. If the liquid level decreases at constant speed V, the time constant as a function of T. We need to find out the time constant for this process, and that happens to be R effective into effective capacitance. Initially, like this is the situation, and this being the middle of the capacitor, and let's say it's been shifted by a distance x, that I would say as V into T. So this will be the one of the capacitor and this is other capacitor. These two were connected in series. So I would say C1 for this much of the part. C1 would be A epsilon naught, distance D, it would be D by 2, and plus this distance is Vt. Similarly, C2 will be A epsilon naught, this distance was D by 2 minus Vt. Since this much of the part is having a dielectric constant, say K, so its capacitance will be this much. Now the effective capacitance of this whole of the system, 1 by C equivalent would be taken as 1 by A epsilon naught, reciprocal of these two portions, it would be D by 2 plus Vt, and plus D by 2 minus Vt divided by K. Or I would say C equivalent, 1 by C equivalent would be 1 by A epsilon naught K here into D by 2 plus Vt into K plus D by 2 minus Vt. From this calculation, perhaps we'll be getting the value of effective C, and now after multiplying R into C effective, we shall have the value of the time constant. So looking onto the option, here I would say the multiplier factor is with D by 2 plus Vt. Here D by 2 plus Vt is the multiplier factor, and in numerator side we shall have A epsilon naught K into R. A epsilon naught K into R, A epsilon naught K into R. So I would say option 1 is the correct answer. Just have this calculation in somewhere in rough paper and you will get this answer. Now let's proceed to question number 5. In question number 5, find the electric field at point P due to uniform charge thin rod of length L having charge Q. Well, this is the configuration. This is having charge Q, and we need to find the electric field at the point P here. First, I would say for this situation, this is the point P, this being the length L here, I would just find the charge per unit length, that is Q by L here. This is lambda. If I'm taking a distance x from here, small length dx, this charge dq would be Q by L into dx. Its field at this point would be dE. It would be dq, that is Q dx divided by L, 4 pi epsilon naught into x square. Total field at this point will be the integral of this term from x is equal to L to 2L. Just have this integral and find the resulting field. Q 4 pi epsilon naught L integral of dx divided by x square minus 1 by x from L to 2L, or electric field strength will be Q divided by 4 pi epsilon naught. This will be 1 by 2L, so it is 8 pi epsilon naught L square. That's the answer for question number 5. That is option 3 is correct answer. Now let's proceed to question number 6 now.